About magnetizing field H and intensity of magnetization I. In the last video we discussed about magnetic moment, and intensity of magnetization is defined as magnetic moment developed per unit volume. Suppose when you apply magnetic field in a given region and there happens to be a material, the total magnetic moment developed in 1 meter cube volume is called intensity of magnetization. So we know that magnetic moment is magnetic pole strength into 2L, or we can also write current into area divided by volume and this magnetic moment we can also write this as intensity of magnetization is pole strength into 2L. Suppose imagine a bar magnet, and the bar magnet is of this shape and the length is 2L approximately and the area of cross section A. The volume of the bar magnet equal to area into 2L. Hence this can be written as area into 2L. When I cancel these two, intensity of magnetization is pole strength by area. In this way we are defining it as magnetic moment per unit volume, and this way it is defined as pole strength per unit area of cross section, pole strength per unit area of cross section, per unit area or unit area of cross section. And the unit of intensity of magnetization, you know that this one intensity of magnetization's unit is magnetic moment unit by volume. Magnetic moment is current into area, which is ampere meter square, by volume meter cube, cancelling this as ampere by meter. Relate three things. H and I are having same units. H and I have same units, or like quantities we can say. So the unit of H, the unit of intensity of magnetization, both are ampere per meter, and the unit of pole strength, which is nothing but the magnetic charge, equal to ampere meter, and the unit of magnetic moment is ampere meter square, not meter cube, meter square. You should be able to differentiate among these three quantities. Now let me talk about the relation between intensity of magnetization and magnetizing field. Usually this field we apply is H and the field that developed is I. So we can say that H is externally applied field, and I is internally developed field. Suppose in a region you apply a magnetic field B, and the intensity of this magnetizing intensity, that means you apply a magnetic field, means magnetic field is externally applied. So we can define H as the magnetic field per permeability, magnetic field by permeability. Hence in free space magnetic field is equal to mu naught times the magnetizing field in free space. Suppose in that space material is there, magnetizing field in that region is magnetic field by mu, which means that in a medium magnetic field is mu times the magnetizing field. Let us say there is a magnetic material up here and you are applying in this region H, hence that is termed as this. Suppose you are introducing a material here. When you introduce a material, because of the magnetizing field H, magnetic moments are developed in this material. So that magnetic moment per unit volume is called as I. So in this region, total magnetic moment or total magnetic field will be actually equal to mu naught times the magnetizing field, the applied field, plus the intensity of magnetization I. So, but you see this I is directly proportional to H. Suppose if you apply more H, then I will be developed more. So they are linearly related. I is proportional to H, which means that I is equal to some constant into H. So I and H are having same units. So this constant has no unit. And this constant is called magnetic susceptibility. Magnetic susceptibility. Magnetic susceptibility means, suppose you have two materials, material 1 and material 2, and you apply H here, the intensity of magnetization developed will be chi1 into H. And in this you apply the same field, intensity of magnetization developed will be chi2 into H. Suppose M2, this field is more than this one, then this field developed more intensity. That means this field is more susceptible to magnetic field. That is why this is called magnetic susceptibility. If this magnetic susceptibility is large, then it is more magnetic material. If this this susceptibility is less, this is less magnetic material. Some magnetic materials are having negative susceptibility. That means when you apply magnetizing field in this direction, they developed intensity of magnetization in the opposite direction. So they have negative susceptibility. So the susceptibility is negative for such materials. Those materials are called diamagnetic materials. When the susceptibility is more, they are called ferromagnetic material. Susceptibility is normal, less positive values are called paramagnetic material. So susceptibility value is negative for dia, positive but small values for paramagnetic material, and large positive for ferromagnetic materials. So we know that from this relation I equal to chi h. So substituting that up here, I know that B equal to mu naught times the H applied plus I can also be written as susceptibility times H. So it is mu naught into H, you take common, 1 plus chi. We are going to pronounce it as chi, but actually this letter's spelling is CHI. CHI must be pronounced it as chi. It's a Greek alphabet. So mu naught times 1 plus chi into H. So this is B. So but this B is what we are talking about, the magnetic field with the material. Here we have discussed magnetic field with the material is mu times H. Hence this can be written as mu times H. So this is mu naught 1 plus chi into H. Mu is mu naught times mu r into H. Comparing these two, we know that the relative permeability of the material equal to 1 plus chi. In other words, chi will be equal to mu r minus 1. This mu r is called relative permeability. And both mu r and chi, they both do not have units.